Hello everyone. The topic of this video is wave scattering. Scattering is a general process where some forms of radiation, such as light, sound, or moving particles, are forced to deviate from a straight trajectory by one or more paths due to localized non-uniformities in the medium through which they pass. Electromagnetic waves are the most commonly encountered form of radiation that undergo scattering. Scattering of light waves and radio waves is particularly important to explain many physical phenomena and the working of radar. Different aspects of electromagnetic scattering have been given different names. Major forms of scattering include Rayleigh scattering, May scattering, Raman scattering, and Compton scattering. Some natural phenomena in which scattering occurs are clouds. We see white colors of clouds due to May scattering. We see blue color of sky due to Rayleigh scattering, and we see the shadows of tree due to geometric scattering.
Now I will describe the parameters of the experiment. We use the computational domain of size 20 by 20 because we cannot simulate for infinite computational domain. On finite computational domain, there will be reflections from the boundary. To avoid reflections, we placed a perfectly matched layer of thickness 1 lambda. We use resolution of lambda by 20 for our simulation. We placed three different obstacles of size lambda by 10, lambda and 5 lambda to observe different regimes of scattering.
Now I will take you through the scheme code used by the MEEP program to carry out a simulation. The first point creates a 20 by 20 simulation domain. Next, we implement a perfectly matched layer of thickness 1 unit equal to the wavelength used in the simulations. Then we create a continuous wave point source located at the point -9, 0. This point is with reference to the center of the computational domain, which is the origin of the simulations. Next, a resolution is set and then an obstacle is placed whose size is varied during different parts of the simulation. The simulation is run for 200 time units, long enough for the system to reach steady state, and the field value of Ez is stored in every iteration. The values for electric field are then plotted for different time instances, and a GIF animation file is created. The following is the result of simulation carried out when the object size is 10 times smaller than the wavelength. As the object is very small compared to the wavelength, there is not much scattering observable in the simulation. This regime of electromagnetic scattering is called Rayleigh scattering. This scattering is inversely proportional to the fourth power of wavelength. There are several physical phenomena which can be explained by this scattering. Some of them include the blue color of sky and the orange color of the sun in the morning.
Next we come when the object size is comparable to the size of the source. In this case, we see that the scattering is significant, and scattering is termed as. In this case, all the wavelengths are scattered equally, and the natural phenomenon when we observe this scattering is the white color of the clouds. This scattering is generally used in cancer detection and screening.
This is the result for large obstacle size. Since the obstacle is large, it blocks most of the wave and forms a shadow in the background. This is called geometric scattering. We have used obstacle of size 5 lambda in this regime. Also in this regime, ray optics holds true. The natural phenomena like shadow can be explained using this. We have identified three different regimes of obstacle size by wavelength in which wave scattering or diffraction takes place. The first, when the obstacle size is much smaller than the wavelength and the wave is essentially undisturbed. The second, when the sizes are comparable and diffraction is evident. Third, when the size is larger and the obstacle effectively shadows the wave.